It's really a pleasure to be here representing our program. You're going to hear from two of us today, myself and Baptiste Fouvry. I want to thank KITP and large for facilitating the program and having us here for 8 weeks. So our hope in the program, our program's exploring the connections between the kinetic theory of plasmas and the kinetic theory of gravitating systems. And we're hoping that by bringing these two historically disjoint but very common fields together, we can sort of leverage what we know. And so I want to give you a taste of that connection, and also hopefully teach you some kinetic theory in the process and something about our field. So you can read the quote at your leisure. We'll get to this plot later in the talk. I just wanted to get that up there. So the title of the talk borrows from two things. One is from a famous writer, but here's two other famous writers. So Chris Hamilton and Jean-Baptiste have done a review recently in Physics of Plasmas, which was focused exactly on this. So like how to translate between what's done in the galactic dynamics literature and what's done in the kinetic theory of plasmas literature. And this was this Plasmaish and Galacticese was in their abstract for the translation. So let's start just, what's a galaxy? It's a collection of a large number of stars, and these stars have potentials that go like 1 over r. So for the purposes of this talk, that's what a galaxy is. What's nice is because I come from plasma and fluid dynamics, I can dip in, insult you, and then leave. So what's a plasma? A collection of a large number of charged particles, all with 1 over r potentials.
I have a question. Is it important if they're charged? Can it be a plasma of neutrons?
No.
Okay.
Yeah. Yeah, I'm not going there. So for the context of this talk, it'll be important that they're all charged particles. Now, if you go down here on this plot to lower temperatures, like molecular clouds or degrees of ionization are 10 to the minus 7, 10 to the minus 6, something like that. You've got dominant species, it's just molecular hydrogen and CO and things like that. You can still do astrophysical fluid dynamics and magnetohydrodynamics in that context, and the magnetic field plays an important role. But you would never describe that system from the standpoint of kinetic theory, because it's very collisional, it's like a fluid. So from the standpoint of sort of kinetic theory, we're going to be talking mainly about hotter systems that are fully ionized or near fully ionized. All right, so suppose you were just starting out and you wanted to describe a plasma or a galaxy in this collection of stars with charged particles, and maybe it was the first time you were learning physics, and you'd write down F equals ma for every single one of these particles. And what I've done is I've just chosen the force to be the Lorentz force law. So there's an electric field which is evaluated at some time, and at the position Ri of the ith particle in your system. So I goes from 1 to n. And there's a B cross B Lorentz force where the magnetic field is evaluated at the position of the charge. And right, you're done, right? If you wanted to do a different system, you would just take whatever the Hamiltonian was, stick that in there. You compute these. From the velocities and positions of the charged particles, you stick them in there, you push forward in time, you solve the electromagnetic fields, you iterate. And that's plasma physics, right? I mean, you all know the problem with this is that there's just too many particles to do this deterministically. So a few issues, just to give you a feeling. There's about 10 to the 28 molecules in this room right now. If you were to store the 3 positions and 3 velocities of all these particles at double precision, this is about 10 to the 18 terabytes. And that's just at one snapshot, right? So it's a huge amount of information. You don't actually want to deal with that many things. Because I do astrophysics, I can, instead of molecules in the room, I can say there's 10 to the 71 protons and the intracluster medium of galaxy clusters, right? So you just don't want to deal with that much data. So that's one issue. One is that, you're not really interested in each particle. Especially in plasmas, you're often concerned with more observable things like the density, the flow velocity, the pressure, maybe the heat transport from A to B and things like that. There are some contexts that Jean-Baptiste would be working on where you do care about each of the particles in the system. But for this purposes of this lecture on kinetic theory, you don't. The other thing is that many body systems are chaotic, meaning that the initial conditions are arbitrary. If I set up a system where I change the initial conditions microphysically just by epsilon, I'm going to get a different microphysical state at some future time. But I don't really want to care about that. So these systems have a they're very sensitive to the microscopic initial conditions, but you want to build a theory where it's not sensitive to the microscopic initial conditions. This motivates a statistical approach. And so you want to ask things like, what's the probability of some particle being at some part of phase space, being maybe within d3r, d3v. So a particle has some position, it has some velocity. You want to know the likelihood that there's a certain number of particles in that bit of phase space. You want to know how that probability evolves. But most importantly, you want to know under what conditions is that probability actually predictive, right? So you want this probability and d by dt of that probability to be predictive. And we all know how this works as physicists. There's no difference between flipping a coin 10 to the 28 times or flipping 10 to the 28 coins one time in terms of the statistics. And so we're relying on the fact that these are many-body systems to be able to sort of deal with the probabilities and then rely on them to actually be predictive of what's otherwise a deterministic evolution. So this is what leads to kinetic theory. And I'm going to sketch out how that goes, and then Jean-Baptiste is going to take it over for the galactic side. So there's a variety of ways into this, but I'm going to follow someone called Klimentovich. And what he said was somewhat of a tautology at first, but bear with me. Okay. So he wrote down this thing. It's not a probability at all. It's a distribution function saying that at some time, at some position, and at some velocity, I'm going to have a particle. And these particles are just point particles, so that's why there's delta functions here. And this lights up if that position corresponds to the position of some particle. I'm using this alpha here just if you wanted to categorize your plasma or gravitating system in terms of different species, like ions and electrons. And the way to think about this is if you laid down some grid, like you were solving this on a computer or something, I don't know, who thinks electrons are blue? Yellow? Okay, here's some, and then, you know, I mean, that I agree. Protons are red. I don't know why. Some kind of synesthesia thing. All right, so that's all this is doing, is it's laying down things in a grid. And if you want to know how many particles are in any given cell, you just integrate over this distribution, and it lights up every time it hits one of these spikes. And so they say, you know, 3 here for protons, 1 for electrons. And this is actually how you solve plasma physics on a computer a lot of times, is that you have something like this on a grid. It's just that your particles aren't delta functions. They might have some finite size shape. So it turns out you can show that this distribution, at least in the context of a plasma, satisfies this equation. And this is just called the Klementovich equation. And it harkens back to those days when you can get your name on something which is obvious. Okay, why is it obvious? So this is just a conservation. This just says F is conserved. I mean, point particles are incompressible, so it's not surprising. You know, you just have particles that are conserved. So this just says that this distribution of point particles is just tabulation. That table is carried around through real space because the particles move. They've got a velocity, and they can shift their velocities because of various forces that are evaluated at the positions. The problem with this is over here, we had 6n equations, right? F equals ma for each particle plus just dr dt is v, and then n for each particle. Right here, we've got one equation, which is great, but it's got 6n dimensions. So we've traded off 6n equations for 6n dimensions. It's just one equation. So you haven't made any progress. This was all deterministic. This is still deterministic. It's just cast in a different form. But the nice thing about this form is it's really easy to coarse grain it to get a statistical theory. So I'll show you how that's done. So the way I want you to think about what we're about to do is that at t equals 0, I've got my electrons, my protons here, and I'm going to write down their Klementovich distribution, and then I'm going to evolve that Klementovich distribution. And then I'm going to take another set of initial conditions. They might be microscopically different than these, but macroscopically the same density, same temperature, all that stuff. And I'm going to do that, and I'm going to plug it through this equation and march forward. I'm going to do this many, many, many times. So you can picture like this bucket of initial conditions, and I reach into that bucket, and I pull out a set of initial conditions, and I run it through the Klementovich equation, and I get out a deterministic answer, and I pick another bucket of initial conditions, and I do this many, 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 many times. And then I'm going to average over all of those outcomes, right? So in this bucket, there could be some distribution, like maybe all my particles are evenly distributed and they're Maxwellian or something like that. I'm just going to call this P of n. It's the probability distribution of these n particles. And so when I do this averaging procedure, I'm just averaging over that probability, right? So what I want to do is, instead of having this deterministic equation, I actually want to average that. I'm going to write it a little different this time, like that. So this is just the Poisson bracket, which is just going to give me the Lorentz force and everything for, you know, the Hamiltonian that I'm interested in. And so this is saying, you know, not what is the outcome, but what is the likely outcome. And the reason this works really well for a plasma is that there's so many damn particles in a plasma that when you do this averaging procedure, you're getting really, really good statistics. And your expectation values are really representative of the actual system, at least to the detail that you care about. So if I go averaging this Kleeman-Towich equation over this bucket of initial conditions, the first thing that you're going to see here is just d by dt of that f. And this thing here, we just call the one particle distribution function. I can see from the timeline. When did we actually start? Do I have 45 minutes, or do we have until 12:45?
Just keep going.
Just keep going. All right, so this is the one particle distribution function. It's saying, what is the likelihood of one particle, just pick a particle, what's the likelihood of that one particle being somewhere in phase space, regardless of everything else? So you just sort of marginalize over every other possibility. And this is the thing that we call little f. Likewise, you could have a two-particle distribution. You can say, what's the odds, something like, we'll call it f alpha beta, which is like a two-particle distribution. What are the odds of particle alpha being somewhere and particle beta being somewhere, regardless of where all the other particles in the system are? So in effect, you're like recursively coarse-graining your system. And, we're physicists here, so you know that I'm not going to write down the three-particle, because, we always stop at second order, if we can help it. So I want to move on. Okay, so if you do a little work, I'll skip a bunch of steps, given the time. If you do a little work, you'll end up with the following equation. So I won't write down the right-hand side yet, but what this says is the likelihood of some particle being somewhere gets carried through real space by velocities and gets carried through velocity space by forces. But the odds that I'm here right now depended on all of you showing up, right? So I wouldn't be doing this to an empty room. It's not what I do in my spare time. So it turns out that there is a right-hand side, and this is what it looks like. And I'll explain this to you. And then we'll move on to something else. Okay. So there's this right-hand side, and there's a few things to look for. One is that you see there's a Q over M and Q over M here. So this is a force. There's a d by dv. That's the signal for, in the PDEs that there's a force. That force, I just took for simplicity to be a Coulomb potential. So that particle alpha is experiencing the Coulomb potential of particle beta. And then there's this combination over here, which, remember, it was the odds of some particle being somewhere at some time, the odds of this particle being somewhere at some time. And then you're subtracting off the joint probability that the two particles are where they are because of one another, but regardless of all the other particles. So if you think about probabilities, independent probabilities just multiply each other. So this is there's some independent probabilities, and then you're subtracting off the total. So this whole thing, we call this, which is a two-particle correlation function. So it's the piece of the probability that's there only because these two know about each other, right? If particles were completely independently distributed, this whole right-hand side would be 0. So if they were independently distributed, the right-hand side would be 0. And this is what we call the Vlasov equation. So we use that all the time. So what you can do, if you weren't happy with that, yeah, sure. Yeah. Yeah, so even if, exactly, even if I have an initial condition where G is 0, just uniformly distributed in Maxwellians or whatever, the subsequent Coulomb interactions will cause correlations. And then those correlations would evolve. Yeah. So if one wanted to brute force this further, you'd write down an equation for G. And given the time, I'm not going to write that whole thing down. But I'll tell you what's in it. Unfortunately, it depends on the 3-particle correlation, right? And the 3-particle correlation depends on the 4-particle, and blah, blah, blah. You know, this is a very common thing in physics. And then eventually you just say, well, I'm just going to truncate it somewhere and, you know, cross my fingers. And you can justify some of the truncation in some cases, but you mainly do it because it's just, you know, you can do something with it. So I'm not going to write down the full G equation, but you can anticipate what it looks like. I mean, there's going to be a left-hand side where this G just moves around in phase space conservatively. You know, this represents 2 particles. Two people have a relationship, and then they walk through their lives, and you know, they have this relationship. But they're walking around in a world where they can form other relationships. So you could have something like G alpha beta affected by something like this. So if one of the partners in the relationship finds a different partner, you know, that's going to affect their relationship, right? If one of the partners in the relationship, if the other one finds another partner, that's going to affect their relationship, right? So if 2 initially uncorrelated particles meet each other, and they interact via a Coulomb potential, that's going to form a relationship. And so this is like a source, and these things are going to end up being dressing. It's just dressing on your past history is part of your dressing for your new relationships. And then, of course, there's 3-particle correlations. You know, if 3 people got together, it'll probably affect 2 of them. I won't say the rest out loud. Okay, so there's a chart of temperatures and densities, and these are typical plasmas, and there's this orange line here. And above that orange line, these systems are so hot and diffuse. Yeah, sorry, JB, I'm going to wrap it up. Those plasmas are so hot and diffuse that, that the kinetic energy of the particles is much, much, much larger than the Coulomb potential that they contribute. And the opposite's true below this line, so there's white dwarfs there, you know, like kind of like metals in a sense. So intracluster medium of galaxy clusters, Sagittarius star, solar corona, interstellar medium, fusion experiments, the center of the sun, all these things are above this line. And when they're above this line, as plasma physicists, you call these things weakly coupled. And what's actually going on above that line is that there's this parameter, lambda, which is just kinetic energy over potential energy. And you can write this thing in the following form, where this is the Debye length. And I think where I will end, I mean, yeah, we really wanted to get to Boles-Glenard and shielding and all that stuff. What shall we do? Don't say it's up to me. Okay, so what this says is that there's a lot of particles in a Debye sphere. And what a Debye sphere is, if I take a positive charge right here and stick it into a plasma, all the negative charges are going to be attracted and all the positive charges are going to be pushed away. And what's going to happen is that your 1/r Coulomb potential is going to get shielded, because the further away you get, that charge is being hidden by all the other charges. So the plasma is polarizable. Gravity systems are polarizable too, but they don't have two signs of charge, so the polarization is very different. So hopefully he'll say something about that. So it turns out when you solve the BBGKY hierarchy, you see this Debye shielding show up. And it's in all these terms which give the dressing. So all these particles, so there's these two particles that are coupled, but one of them interacts with this entire bath of surrounding particles, and that's the dressing, that's the shielding that you see. And this particle operates on all the other particles and interacts with it all in the bath, and that's the Debye shielding that you see. So a way to think about this whole right-hand side in a plasma is it's telling us that we shouldn't think about a plasma as being composed of charged particles. We should think of the plasma being composed of Debye clouds. So these spheres of charged particles that come along as dressing for every single particle. And it's because of that, the fact that this number, sorry, this is, nobody stopped me here. It's the fact that these numbers are so large that you can form the statistical theory, and it's also the means by which you truncate this BBGKY hierarchy, and so on. So I think I'll probably stop there and transition to JB. The only thing that I'll say is that you end up with this right-hand side, and that's been worked out by these two gentlemen independently, Bolescu and Lenard. So this is called a Bolescu-Lenard collision operator. And there's a long history of this in plasma physics, but there's also a history of this, but more recently in galactic physics. And that's where I'll turn it over to JB.
I'm aware of the time, so I will be quick, dirty, and laid back, obviously, because I'm French. You can see it from my accent. So let me just start the timer. And so essentially what I will plan on do is to justify why we have this program going on, justify why we say galaxies and plasmas are the same thing, and justify why it was a good thing we got this funding, because there are still many open problems regarding both plasma dynamics and galaxy dynamics. Matt has done a great job of laying down the ground, saying that indeed there are deep similarities between plasmas and galaxies, and as wrote it down, it is not limited only to the fact that the two interaction potentials are the same, but similarities are much deeper. So what I will do is, Matt described what is a plasma, so I will give you two examples of a self-gravitating system, which more generically are examples of long-range interacting system. I will redo everything Matt has done in a dirty, few steps way, and show you every of the key dynamical processes that can be described this way. So first example of a self-gravitating system is a very famous one, which is actually called the Milky Way. So it's a galactic disk composed of stars orbiting together within essentially the same orbital plane. So if I was to do a drawing of the Milky Way, what I would do is I would simply draw a plane. I would ask for my star to move within this plane with essentially every one of them the same orientation. This system is composed of n equal 10 to the 11th star, which is going to be much smaller than the lambda parameter that Matt mentioned. The dynamical time in this system is about 10 to the 8th year, which is typically the time it takes the sun to do one rotation around the center of the Milky Way. So this system is said to be cold, dynamically cold, because orbits are a bit boring. They are essentially circles, and every of them are aligned. And this system is said to be young, because 10 to the 8th year is actually not that short compared to the age of the universe. So this is a galaxy. Another example of self-gravitating system is what we call a globular cluster. You take stars, but you allow them not to be aligned with respect to one another. So it's just a bunch of stars which are orbiting together with respect to one another, forming a big spherical cloud of stars. This is what we call a globular cluster. And in a sense, it's a much more collisional system compared to a galaxy because the number of stars is much smaller, 10 to the 5, and the dynamical time is much faster since it's only 10 to the 5 years. So compared to a galaxy, this system is said to be dynamically hot because orbits are not circle and orbits are in every direction. And this system is said to be old or collisional because this is much shorter than the Hubble time. And so the goal of kinetic theory is to devise setup or framework within which we can describe this whole range of systems and setup within which we can use all the methods that stems from plasma physics. So how can I rephrase everything that Matt has said in a very, let's say, simple way? So this falls within the range of what we call long-range interacting system. Plasma are long-range because electrons can couple to electron essentially as far as they want. Should we forget about the bi-shielding? And stars can couple to one another as far as they want because the gravity cannot be screened. So what you do in this context is you work with it generically what I call phase space. I want to say very generic because this applies not only to 3D system, but it applies to much more generic class of system. So these coordinates are generically called Q and P, or in the case of plasma, it's position and velocities. You take n particle, which a mass, with a mass that is set essentially by my small control parameter, which is 1 over n, and then I allow every of my particle to interact with one another. And so, as Matt emphasized, the key element to describe the system is what is called the empirical distribution function. He really emphasized empirical in the sense this is one realization of my system, and it is simply set by being lazy and putting a Dirac delta at every position of the particle. So you take your system, you know where are your particles, you put a Dirac because there is zero uncertainty so as to where they are. And in a sense, I'm looking at my system from above in phase space. So this would be phase space, and I put a Dirac delta in every places where there is a particle. Once you've sufficiently step back and have described your system in this very formal way, you can, in a very lazy way, write exactly what got Newton obsessed, which is the n-body problem, which in this framework takes a very simple form of, so I write it explicitly. And so this is done. I've described exactly the n-body problem, the empirical distribution streams within the empirical Hamiltonian. And again, you can see that we are super smart in galaxies because this equation is the same as Matt wrote down, but I will not bother writing electric field, magnetic field, exploiting the Hamiltonian. This is coordinate free, probability is conserved, and I do not need to specify the coordinate within which I'm working. Of course, as Matt emphasized, this equation in a sense contains too much information. It's exact and perfectly deterministic. And so what we are generically interested in is, in some sense, what would be the average dynamics. So this is what Matt emphasized via its average over initial condition. And so in a weak or in a vague sense, I'm going to expand Fd as an average value plus some fluctuation around it. I will not tell you what is precisely meant by this, and this is also something that we extensively discussed during this program. So once you've done this, or what you say, my system is some average representation plus fluctuation, I can see pile up all the processes that this sort of approaches can describe. So the first process we can describe with this big machinery is what's called mean field dynamics. And I want to stress this point because I think this is a key equation for people involved in dark matter description. So the mean field dynamics is simply this equation. So the mean distribution function is evolving within the mean Hamiltonian. It seems I've not done much, but do look that I've split an average. So this is called the Vlasov equation. This is called the collisionless Boltzmann equation. In a vague sense, this is called the Liouville equation. And for example, understanding precisely the characteristic of this equation allows one to describe a famous process called violent relaxation. So should you be an expert of this equation, you would be in a position to use it and predict the origin of the NFW profile. If I've described the average dynamic, now I can ask myself, what is the leading order dynamics of the fluctuation, delta F? So this is the dynamics of perturbation, which again, since I'm lazy, I'm just going to write it in this very formal way. And it takes the following form, where the dynamics of the fluctuation is going at leading order to be solved by two effects: the mean potential and then collective effects. Again, I don't want to go into specific, but everything Matt has said, this is going to drive the bi-shielding, and this is going to drive what is called phase mixing. It's just when you cross someone on the highway, you're phase mixing with it. This equation is a crucial equation. It is also a crucial equation we're discussing in this program. It is the one that governs linear response theory. So how do fluctuations get amplified by my system? And so if you want to understand the origin of spiral arms in galaxies, this is the one equation to look at. Of course, as I told you, the number of particles in my system is actually quite limited. So I do not want to limit myself only to the dominating dynamics of perturbation, and I want to go one step further, which is to go to collisional dynamics. So this is where Matt stopped. And so again, I'm lazy, so I will write this in a very formal way. So this is what we call collisional dynamics. So collisional is a tricky word, because it does not mean I have hard-on collision as I would have in a gas. Collisional means my system is aware of its finite number of particles. So collisional means there will be a place where I will put 1 over n somewhere. And so what is the collisional evolution equation for my system? It's simply written like this. In a sense, I've broken, in a vague sense, the conservation of probability, and I ask my mean distribution to be aware of itself. So this bears many famous names. The Chandrasekhar equation is exactly of this form. The Landau equation is exactly of this form. The Balescu-Lenard equation is exactly of this form. And it is the equation that tells me my system, being aware of its finite number of particles, has unavoidable Poisson fluctuation in itself. This Poisson fluctuation can couple to one another. So the function G alpha beta, the excess of probability Matt emphasized, will unavoidably drive the relaxation of the mean distribution. This equation is the one that is responsible, for example, for radial migration in disks or the gravothermal catastrophe in a globular cluster. Of course, I've been lazy, so you could ask yourself, is this just purely formal, or can he be more explicit? The answer is yes, I can be more explicit, and what essentially I will try to emphasize is that, in a sense, a galaxy is a plasma, provided you look at it in the good variables. And this is really one of the cornerstones on which this program is oriented, which is the leverage of the deep similarities, or the deep structural or topological similarities between galaxies and plasma. So when I was learning physics in undergrad, I learned one important example, which is the harmonic oscillator. I will say it one last time. I'm very lazy, so I will stick with the harmonic oscillator. So the Hamiltonian of the harmonic oscillator is kinetic energy plus external potential. Again, the good place to look at this system is in phase space, so I should draw the phase space diagram of the harmonic oscillator. And in this space, the trajectories of my particle are simply concentric circles. This is complicated. This gets me too dizzy to look at, so I should find an easy way to model this system. And so the easy way is to label every of the circle with a variable which we call the action, And once you've specified the action, once you've specified the orbit, the position of the particle along its orbit is given by another quantity, which we call the angle. This is a key step. This is where the magic happens, and this is where I transform a galaxy into a plasma. If I look at the phase space diagram of a harmonic oscillator in angle action space, this is what I obtain. So the angle and then the action that go from 0 to 2 pi. And I simply see that my particle is streaming along a constant line. So that's fascinating. So I've really transformed complicated trajectories into simple trajectories in phase space. So this is the galaxy version of the phase space diagram, and the version for a homogeneous plasma is actually very similar because particles, in the absence of perturbation, also stream along a straight line. So if you're able to do the change of coordinates from position velocities to angle on action in a galaxy, you've transformed your galaxy into a plasma. Leveraging this one change of coordinate is absolutely instrumental in this program and in being able of tailoring plasma method to galaxy and galaxy method to plasma. One key quantity, which I forgot, is the velocity or the frequency with which a particle in this space is streaming along its unperturbed orbit is set by what we call the orbital frequency, omega, which is a function of the action. In the similar way, the tautology here is that the frequency here, v, is actually v of v, which is a deep relation. It just tells me at a fixed velocity v, you explore a position space at velocity v. And so from this, now I'm done. I can do the translation of plasma to galaxy and galaxy to plasma. So this is what I will briefly write here. So on the one side, I have plasmas. On the other side, I have galaxies. So in a plasma, the good coordinates are position and velocities. And this is what Matt kept focusing on this quantity to describe the state of the system. In a galaxies, those are angle and action. Then the other elements to translate are associated with frequencies, which are velocities in plasma and simply orbital frequencies, the same as, for example, the Keplerian frequency. It takes 1 year for the Earth to revolve around the Sun. And importantly, the distribution function for my system, in the case of a plasma, it amounts to describing the evolution of the distribution function in velocity space, while here it amounts to describing the evolution in action space. So I have only 5 minutes to finish this 20 minutes. So we failed at explicitly writing this collision operator, which is called the Balescu-Lenard equation. We failed at describing all the physical processes it contains. We failed at convincing you that it does work in some regime. For example, it has been explicitly shown in astrophysics that it describes radial migration in disks, eccentricity relaxation around supermassive black hole, or even the contraction and core collapse of a globular cluster. Yes?
Sorry, one question. So the gravitational system is universally attractive and the plasma one is not. Is that philosophy?
No, it's very important. It just means that you need to do the translation correctly. So if I was Matt, I would say, okay, let me write, for example, for some of those it will make sense. The dielectric function of a plasma, would this make sense? Which is essentially 1 plus dv df over v minus omega. Okay? Let me do the galaxy case. It will be a marvelous modification. It's done. I've done the translation because I've switched the sign of interaction. Yes, indeed. Indeed, this is very important. In gravity, you cannot screen the interaction. And so the equivalent of what's called Debye shielding for math, it's called gene instability in a galaxy. And so in a galaxy, as long as you look far away enough, it will unavoidably be unstable. It will unavoidably collapse. Yes?
If we're doing questions, are we doing questions? Okay, so my question is that you said that the galaxies are gauss in everything.
Yes.
And so J is evolving, right? It's not actually a straight line like that. The actions are changing.
Yes, yes.
So do the plasmas also have that commonly in their solutions?
So velocities or average velocity of plasma do evolve. And we are playing a bit of a dangerous game if I have to answer the plasma question, so I should let Matt answer the galaxy questions. But yes, it's the same idea. It's the same idea. Yes.
So you do perturbation theory on the orbits, or?
Exactly. So I was just finishing up with listing the failure of this formalism, and so in the interest of continuing with this list of non-achievements, I wanted to conclude with topics we will be focusing on during this program, which are topics which are for now not yet within reach of our formalism. So why is this equation actually not the master equation solving every of the problem we can face in a self-gravitating system? So there are a couple of those, and I wanted to emphasize maybe only 2 or 3 of them. So I've convinced you that the harmonic oscillator is a seminal example to describe the change of coordinate from position, velocity to angle action. But it does assume in a very strong fashion that my system complies with integrability, which means the Hamiltonian is not too complicated. The Hamiltonian is topologically simple enough so that I can construct angle actions coordinate. Bad news, this is not correct for real, genuine self-gravitating system. The galaxy is a thick disk, so I cannot exactly construct angle action. Dark matter halo are not purely spherical. I cannot exactly construct angle action. And this has the impact that orbits within non-integrable potential explore much more efficiently phase space, for example, leading to chaotic diffusion. So this is obviously a place where kinetic theory is failing. There is another problem which is called degeneracies or dynamical degeneracies, which is the fact that in a plasma, particles are never stopping. They are streaming at the velocity v. But in a self-gravitating system, I can devise a system where the orbital frequency is always 0. These are not nasty, purely academical questions. It does occur when you describe the relaxation of orbital orientation around supermassive black hole. In this regime, formally, if you look at it, this is the same question that appear when describing strong turbulence theory or gyrokinetics in some limit regime, and those are related to renormalization theory. Again, this is a topic where this vanilla approach does not work. There is a key other regime where we are currently severely failing, which is the one that is called marginal stability. Marginal stability stems from the fact that a galaxy is initially linearly stable. If you poke it, it will not explode. But as time goes by, this system wants to go unstable, phrased physically. As time goes by, galaxies want to form spiral arm or want to form bar. And marginal stability is exactly the regime where Matt's Debye shielding starts to get crazy. Divergences or unphysical divergences pop up in the kinetic equation, and for now we do not know within the field how to precisely describe those. These are linked to what is called nonlinear trapping, mode particle coupling, weak turbulence, and bifurcation theory. I'm not only name dropping, I'm just trying and list topics which will be topic of discussions here. And finally, the last regime which we are not yet, on which we do not yet have a full grasp, is the one associated with large deviation. Matt heavily emphasized the idea that your exact system, which is this empirical distribution, FD, you want to describe it in an average sense. And this led us to describing or to obtaining a kinetic equation for the average distribution function. But I don't care about the average distribution function, I care about the one Milky Way I am observing. And so the question is this average kinetic theory any informative with respect to one realization of one particular system? And so in the realm of large deviation theory, what we do We emphasize the fact that it does depend on a small parameter. It tells me the jitter between different realizations. And we introduce an average of this quantity of the empirical distribution function with respect to the angle. So this thing looks very similar to F, but it does change from one realization to the other. And so this is my Milky Way, and this is an idealistic ensemble average Milky Way, which I will never have access to. And so the question is, what is the dynamic of the angle average distribution function? And we can show in particular that it satisfies a Langevin equation of the following form. The stochastic angle average distribution function has a collision term in the same way that the ensemble average has, but it is also sourced by another source of noise that tells me, well, maybe the bar of the Milky Way appears now, maybe it will appear in 10 million years, I don't know, I need the statistics of this. And so it offers me with this finite diagram, where here I would represent the distribution function of my system. This is the boring evolution predicted from the 60s of the average distribution function. This is the reality, which is my average distribution function. I want to know what are the size of this jump, and I want to know what is the correlation of this jump. How likely was it for the bar of the Milky Way to have this phase or this one amplitude? And so final remark, I hope we vaguely managed to convince you that plasmas and galaxies share deep similarities. I hope we vaguely managed to convince you that the field is surely not solved, and there are many topics to be discussed among these two communities. I could have listed many other topics like orbit average, gyrokinetics, all the aspects related with n-body simulation, phase-space turbulence, etc. And obviously, this sort of motivation should emphasize the need for a stronger interconnection between these two domains, which is the reason interconnection is within the title of our program. Thank you.
More questions? I guess all decided to answer them. Please.
Can I say maybe not a question of comment? So as someone working in Galaxy, we use phase distribution function and all of that for XV as well. Actually, it's probably used more common in XV initially, and now switching to action-based. That's what I used to feel. So a lot of like to infer the mass profile, potential, gravitational potential of the galaxy, we use the distribution function on the left. Very
Yes. Because no, it's historical and it's legitimate because it's easy to observe. This is what you observe. But this is not where dynamics shines in the simplest form. Yes?
My understanding of the averaging is over some initial conditions, is that right, in the first part of the talk?
Yes, so Matt should come up and answer.
So what I want to ask you,
Yes.
when you're talking about the galaxy, the F or the galaxy,
Yes.
averaging over cosmological initial conditions, or what do you have in mind in terms of the initial conditions for the galaxy?
So this would be just you, for example, if you are doing only numerical simulation, this would be you changing the random seed of the run. And your question actually is a very delicate question, is what exactly do we mean when we observe the galaxy and what is exactly the distribution function? Nonetheless, given that Gaia has observed this spacecraft has observed millions of galaxies, it would be illegitimate to pretend that there is no some distribution function we can observe from the data. When you look at it and bin it or coarse grain it on large enough scale, it's obvious there is a distribution function, and it is indeed this one-body distribution function that we have in mind here on this right-hand side. Does this answer? Vaguely.
One question about the perturbation aspect that you wrote down. So in what way, I guess, first we can think of it as a maybe some steady state system, but with added perturbations like satellite or galaxy coming in.
Yes.
I was wondering, are there some limitations in that form, or like somewhere down the line to kind of how big of perturbation can be well described with the system, or kind of there are like different tactics for like as a function of mass of the
Yes.
satellite galaxy?
So I erased the perturbation evolution equation. But I should have emphasized it's a linear perturbation evolution equation. So I've ordered the perturbation by their scale, and I threw away anything that is second order. If you kick it hard enough, this cannot be described by linear perturbation theory. And Milky Way is nasty because when you look at the typical over fluctuations, let's say of 10%, 20%, it's not within this linear response regime. And so if you start and have too large perturbations, then describing your system with having a nice mean field potential is worrying, and neglecting any nonlinear effect associated with this large amplitude is worrying. And observations also point out to the fact that no, there is no free lunch, and you are not in this nice, smooth, linear regime.
Yeah, and so that's my question. Okay, I guess that's kind of expected, probably, but is there kind of a criterion or a condition that, yeah, kind of how would you write down requirements that you are like in the linear regime versus nonlinear?
I think the lazy answer would be depend on the cases. So I would not be able to answer immediately. What I know for a fact is that if it's not okay, I will ask you to reduce your amplitude by a factor 10. I check again. If not, I will reduce. And ultimately, I will be okay.
But we also do have ways to treat strongly detached systems as well.
Yes.
It's not all hopeless. It's just that this precise approach doesn't work. There's other ways to do it.
Yes.
Okay, well, maybe will that be a topic of further discussion, maybe this week or next week?
I think you can bribe Chris Hamilton over there, so I'm pointing at him to discuss this. No, it's related, for example, let's say you take a toy model is, you take a galaxy that is unstable, so it wants to form a spiral arm. Okay, but the fact is the universe is finite, so the amplitude of the spiral arm cannot grow to infinity. It will stop and saturate. It's nonlinear effects, in particular nonlinear effects associated with trappings that are responsible ultimately for the saturation of this amplitude. And the good news, it's not directly within this approach, but the good news is we now have a handle on how to precisely predict what should be the saturation amplitude, how much nonlinear or how much crazy your system can go. So this can be made explicit.